All right, next up we have Jose Antonio, who's a student at the University of Maryland. Today, Jose will present on autonomous quantum refrigerator resets for a superconducting qubit. And this research was conducted with Nicole Younger-Halpern and Simone Gasparinetti.
Yes, hi everyone. Thanks for the presentation and to the Duke folks for this very nice workshop. Yes, I'm going to be presenting this experimental collaboration with Simone Gasparinetti's lab at the Chalmers University of Technology. So Amir, Paul, and Simone conducted the experiment. We worked on the theoretical modeling of the device. Yeah, so I'll begin by sort of giving a motivation by talking a little bit about quantum thermodynamics, which has been a field that has seen a history of triumphs in terms of foundational results, like extensions of the second law to microscopic systems, enhancement of thermal tasks due to intrinsically quantum phenomena. But in terms of real world, like technological applications, quantum thermodynamic technologies are scarce. So we study autonomous quantum machines to deal with this. Autonomous quantum machines perform tasks without time-dependent external control. This means two things. From the thermodynamic perspective, it means that a protocol doesn't need a work input. And from a practical perspective, it means that mid-protocol, you don't need direct meddling with the device. So as there's no work input, you need some free energy source, a non-equilibrium free energy source, which abundantly is an access to heat bath at different temperatures. The task that I'm going to be talking about today is qubit reset in superconducting circuits. I'm going to begin by giving a little bit of context on superconducting qubit reset, talking about our system, the experiment, some particular results, and a bit of an outlook. So one of the Vincenzo's criteria for a device to be actually called a quantum computer is the ability to prepare known available reference states. A very intuitive way to think about these preparations is simply taking energy away from qubits and leaving them in their ground state. And the metric by which this task success is quantified is by measuring the target qubits excited state population. Superconducting qubits, of course, are one of the leading platforms in quantum computing. So, of course, very smart people have been thinking about these kinds of things for a while. And the main protocols for reset are active reset and unconditional reset. So in an active reset, you perform a measurement in a device and then apply a gate. And in an unconditional reset, some rapidly decaying state is prepared by a pulse sequence of some sort, which leaves the system of interest depleted of excitations. Now, autonomous reset contrasts with these two protocols, since these two protocols directly require time control, right? Active reset is completely feedback dependent, and in unconditional reset, you need a pulse sequence of precisely timed pulses in order to execute the reset task. Now, one may think like, okay, well, what's wrong with passive thermalization, right? If I just let a qubit evolve to its own devices, it's gonna naturally relax. That is true, but the final temperatures that it will reach are kind of high. And most importantly, in order for it to reach this final temperatures, you need to wait for hundreds of microseconds, several relaxation times of the qubit, which, if we're thinking about implementing reset protocols in actual information processing devices, and we need to wait for hundreds of microseconds for every information unit to deplete itself, that's very bad news for a scalable device. So in this project, we worked on the well-known thermodynamic protocol of absorption refrigeration. applied to the context of qubit reset. So the setup of our system, we have 3 qubits with frequencies omega 1, omega 2, and omega 3. And the middle one is a qubit. So the gap between the ground state and the first excited state of this qubit differs from the first excited state and the second excited state's gap by some harmonicity alpha 2. And these are linearly coupled with each other. The frequencies of these qubits fulfill this resonance condition, meaning that the energy of the leftmost qubit and the target qubit matches the energy of the most excited state of the middle qubit. The leftmost qubit is going to be coupled to a waveguide that acts as a thermal bath that is populated with thermal photons with an average number in H. It's going to be coupled with a decay rate gamma 1. And the qubit is going to be coupled to another waveguide with a different average photon number, NC. Now, this subscript, I'm sorry, were chosen because this is going to represent a hot bath. This is going to represent a cold bath. And the rightmost qubit is the target qubit. That means this is going to be the qubit that we're going to be interested in resetting. And yeah, these Bose occupation numbers directly translate to temperatures. These are the experimental parameters of the device. The omega values are typical for superconducting qubit architectures, as well as on harmonicity. And the decay rates, I'm going to point this out since it's going to be relevant later. The decay rate of the cold qubit into its bath, it's considerably larger than the decay rate of the hot qubit into its bath. We can write this as the system. The dynamics is described by a microscopic Hamiltonian that includes the free part of each qubit, including the unharmonicity, the corresponding unharmonicity of the middle qubit, as well as the nearest neighbor couplings of the qubits. So I'm going to refer to the joint state of the 3 qubits as IJK. And the resonance condition is going to single out 2 particularly relevant states. One is the state 101, where excitations are concentrated in the hot and target qubits. And the other one is the state 020. These 2 states, because of the resonance condition, have equal energies and are going to be coupled with some effective coupling strength A, which is measured to be around a few megahertz. These transitions between 101 and 020 are going to be dominant once the resonance condition is fulfilled. And thus the dynamics of the system can be approximated well by this effective Hamiltonian that only takes, like its interaction term only takes into account the coherent exchange between these 2 resonance states. So for our initial conditions, we assume that both the hot and cold qubits are thermalized with the respective baths. And this is going to be important because these thermal states that the qubits begin in are mixed states, but the presence of the baths is going to bias the system, even though it's in an overall mixed state. It's going to bias the system, have excitations in the hot qubit, and it's going to bias excitations out of the cold qubit. On the other hand, we assume that this target qubit, it's in its worst possible scenario, it's completely excited and we wish to deplete it. And yeah, so the 3-bond interaction in which excitations in the hot and target qubits are exchanged with the cold qubit's most excited state is going to be a relevant component of our refrigeration protocol, because our target is going to be reset by 2 processes. First, the coherent coupling between these 2 levels, and second, the dissipation of the cold qubit into its waveguide. Now, as I pointed out, this decay rate is larger than other coupling rates in the system. So the refrigeration protocol, in summary, works like this. You connect the 2 heat baths that biases our system towards the 101 state. 101 and 020 are coherently coupled, but excitations from in the cold qubit are rapidly dumped into the waveguide. So this coherent process actually doesn't flop back to 101, and that's going to deplete our target qubit. So this is the refrigeration protocol. I'm gonna talk about how it actually works. So this is probably like the main plot of this presentation. So in the x-axis, we have the duration of the protocol. Even though the lines look broken, it's because in the second part of this plot, we're zooming out. So these lines are all continuous. And on the y-axis, we have the reset metric, which is the excited state population of the target qubit. And these different shapes denote different experimental data points for different thermal photon numbers in the hot bath, which translate to different temperatures. This is an increasing function, so a higher photon number means a higher temperature in the hot bath. Now, these particular lines that are there, the green dashed line represents the target residual excited state population, which means this is the excited state population that the target would reach if left to its own devices. And the blue dotted line represents the excited state population if the target were connected to the coldest path available. So notice that both, like the theoretical curves, which are the solid black lines, and the experimental data points, even for low-ish hot bath temperatures, our refrigeration scheme is going to beat passive thermalization even if the coldest bath available is the one used. So this whole setup of having a resonance condition, having a rapidly dissipating mode, and all of this, it's justified by this outperformance of passive thermalization. This cooling protocol is also considerably faster than the target's natural relaxation time. I'm going to touch a little bit on this later. Now, in order to analyze the operation of the system, of the device, we use the metric of the steady state population, which we define as the population after a long time, which we take to be a little bit over 100 microseconds. This may seem arbitrary, but it's really justified when you look at this. Like the curves don't really fluctuate or decay significantly after this time scale. So taking 100 microseconds as the time scale at which the system reaches its steady state is reasonable. And we look at this steady state population as a function of the hot bath's temperature. So with increasing hot bath temperature, this final steady state population that is reached is decreased. And on the other hand, if you keep the hot bath's temperature fixed and increase the cold bath's temperature, we notice that this actually hinders the reset protocol. So this actually makes sense. Remember that at the beginning of the talk, I said about how we're substituting a work input by, in this case, a thermal gradient. So if we have a very dramatic thermal gradient that gives the system a lot of free energy to perform its reset task, but if the temperatures are comparable to each other, the reset protocol can't actually be that good. And this also shows that these bath temperatures are sensitive parameters for the protocol's performance. Yeah. So in order to benchmark this a little bit thermodynamically, we'll look at the coefficient of performance, which is how much heat we can get out of the target compared to how much heat it's leaking out of the hot bath. And we find that for a representative set of temperatures, this is 0.7. This is great. The second law of thermodynamics is still standing. And this coefficient of performance might seem somewhat obscure, but it's just similar to a classical absorption refrigerator, which is simply a normal, ordinary AC system. We look at further figures of merit. Let's recall the state population definition. In the experimental data set, we observed this to have a minimum of 3 × 10⁻⁴, which translates to an effective qubit temperature of 22 millikelvin, which is close to the theoretical prediction for this device. And the reset time, which we define as the time scale at which the population reaches 1%, the lowest reset time we found was 970 nanoseconds. So when compared to the target qubit's natural relaxation time, which for this particular device is around 17 microseconds, we notice that this refrigeration scheme is actually very much superior to passive thermalization. So this is a proof of principle demonstration of an autonomous quantum machine that performs a protocol that is usable in quantum information processing devices. And it's not just like a quirky thing like, okay, yeah, we can do this without time control, but it's kind of bad. It's not that type of situation. This actually, in terms of reset fidelity, is performance competitive and even outperforms like the state-of-the-art non-autonomous protocols for unconditional reset, which are those two references. Although the reset protocol's reset time for unconditional reset is still superior than our protocol. So our protocol is way faster than passive thermalization, but it still doesn't beat non-autonomous protocols, even though it has a better reset fidelity. So as for the outlook, what lies next? First, optimization. And I don't really want to get into details here, so I'm just going to quote our experimental collaborator, Simone, who said that, yeah, we're just trying to build an autonomous quantum refrigerator with the Lego pieces that we have laying around in our lab. But this particular device wasn't tailored for this particular task, so there lies an opportunity of improvement. And also, since this autonomous protocol was competitive, we've also been thinking about what autonomous quantum machines and protocols can be thought of beyond this. So Markus Huber's group in Vienna has worked on autonomous quantum clocks. So with a similar setup to this, in which you have three-body interactions, you can engineer a heat engine that works as a clock in some contexts. And we've also thought about general criteria. We joined forces with Markus Huber's group and thought a little bit about autonomous quantum machines in a more abstract manner than this particular instance of a device. And something that I've been working for quite a while now is thinking about gate protocols that perform logical operations in current devices without the need of time control. So that's the end of my talk, and I'll be happy to take any questions.
All right. Questions for our speaker?
So is this optimized for like, it's supposed to be a scheme for like fixed frequency qubits or also flux tunable qubits?
Yes, so this,
Maybe you can repeat the question.
yeah, if I missed something, please let me know. He asked about if these qubits were frequency tunable. So one of the important experimental parts that I omitted in this presentation is the fact that the hot and target qubits are taken to be frequency fixed, but the middle qubit is frequency tunable, so that's why the omega 2 has like this superscript. Yeah, so an important chunk of the paper that again I didn't include here is the fact that proving that this protocol is optimal for this resonance condition. So yeah, the cold qubit is frequency tunable.
My follow-up is, if we can tune these, then what's like how much is the advantage of having this hot qubit? Like, why not just couple the target to a cold qubit, like directly on resonance, like a 2-qubit system instead of a 3-qubit system?
You mean not having the hot qubit at all?
Just put cold and target qubit on resonance. If you can just tune their frequencies, and then like dump the target excitation onto the cold qubit.
I mean, the main thing that drives this device is the presence of this hot bath. So excitations are coaxed out of the target due to the heat flow of, the heat leaking out of this hot bath. So, yeah, the presence of these baths is what drives like this nice initial, what biases the system to be close or similar to this nice initial state 101, and that's what drives the refrigeration process.
I guess my question is, why use the 101 to 020 coupling rather than just a 10 to 01 coupling to drive a dissipation?
Can you repeat that? I'm sorry.
Why use the 101 to 020 coupling rather than just have a 10 to 01 coupling?
I guess my immediate response would be that the presence of the heat bath plus the the mismatch between these two couplings is what drives the refrigeration protocol. If you don't have, to say so, like a decay rate that beats another decay rate, like controlling the protocol itself is going to be difficult.
Thank you.
Sure. So for that question, I think if you do that method, you're limited by your cold bath. So your preparation of the target will only reach the cold bath temperature. But by having the hot bath, you can do refrigeration and get to a temperature lower than your cold bath.
That makes sense.
Yeah.
Isn't this the work that you're using to pull that down has come from the hot to the cold? That's like generating the work, I think.
My question is, you still want to turn the reset on. So I don't see so your argument was like the autonomous thing relative to the other ones are like time independent. But you don't want autonomous reset on all the time. So you'll want to say tune this thing into resonance, maybe.
Yes, but okay, and I'm gonna cheat a little bit with my answer here. You're seeing this reset protocol simply as some part of a larger information processing device. So you tune, you just tune your connections to the heat bath, reset it, and you have a one-shot protocol that gives you a pretty decent fiducial state. But yeah, this is not, this is, the appeal of this, I would say, is that you have this autonomous protocol that mid-protocol you don't have to meddle with it, but it's not it's just a one part of an information processing device. I don't know if that makes sense.
It makes sense. I just think when I think about doing reset, it's always going to be temporal. Because most of the time I want the qubit to keep its information. And I'll always have to flip some switch to turn on my recess process.
Yeah, maybe we could ask, how would you turn the reset on and off? What would you have to add so that it's reset? You could flip it on so it's in reset mode, or flip it off so it's leaving neutral?
I would say that you can turn this on and off by switching connections to heat baths. So this protocol is very sensitive to what temperatures you have to work with. So if you're done or if you want to, stop your reset or something, you could just connect to a different layer of the dilution fridge that this is mounted on, and that would, stop your reset protocol.
I think this is a follow-up to the question, how do you actually introduce the heat baths, or is it tunable? Like, I assume you are not actually connecting to the different, stage of the dilution fridge. Like, wouldn't that introduce a lot of heating into the fridge?
Yeah, so in this particular experiment, these heat baths are enacted by waveguides that you populate with some photons that are thermal in a small range.
Okay, so you drive.
Yes,
it. Okay.
but that's a proof of principle. These are not real heat baths. This is just quasi-thermal noise, to say so in a way. But imagine that you have a black body radiation curve. You're interested in it being thermal just in a small range. That's what we're doing with this synthesized noise. But you can turn off different parts that you're not interested in of the black body spectrum by connecting filters, for example. The experimental details of that, I owe them to you, but yeah.
All right, so let's thank the speaker again and all the speakers.